Hello and welcome to this video on finding a minimal spanning set for a subspace spanned by a set of vectors. So in this video, I'm going to first start off by defining what it means for a set of vectors to be a minimal spanning set of some subspace of vectors. And then I'll go over a quick procedure on how to determine, how to find this minimal spanning set for a subspace. And then the last bulk of the video, I'll be going over several examples in which I'm given a set of vectors and then a subspace, which is the span of that set of vectors. Hopefully you recall that the span of a set of vectors, or the collection of all linear combinations of a set of vectors, is indeed a subspace. Alright, it's a vector space. And what we'll be doing in these examples is finding finding a minimal spanning set of the span of the set of vectors. Alright, which is the title of the video. Okay, so my first page here is just a definition. What does it mean for a set of vectors to be a minimal spanning set for some subspace? So minimal spanning sets. Okay, so a set of vectors, we'll say called S, that spans a subspace called W. Alright, meaning that this W is the span of S, right? W is made up of all the linear combinations of the vectors of S. So a set of vectors S that spans a subspace W is called a minimal spanning set for W if there is no smaller subset of S that also spans W. Okay, so if there's, so that means, is this the smallest number of vectors whose linear combinations all, make up W? Or could I find a smaller set of vectors such that W is made up of all the linear combinations of those, right? So another way to put this with some notation, if the span of a set S is equal to subspace W, or if W is equal to the span of S, and there is no other set called T that's a smaller set of S, right? A smaller subset of S, a proper subset. That's what this sideways U symbol means, right? So it's basically S with some, with some vectors removed, at least one vector removed. So if the span of S is equal to W, and there is no set T that's a proper subset of S, a smaller subset, such that the span of T is W as well, then we would say that S is a minimal spanning set of W, right? It's the smallest set of vectors whose span is equal to W. Great. Now, this procedure I have on the next page for finding such a set, I'm going to go through it on the first example or two in detail, but then I'll also show you there's actually a pretty quick way to determine a minimal spanning set for the span of a set of vectors, right? For the subset, for a subspace that is a span of a set of vectors. All right. So procedure for finding a minimal spanning set. And like I said, after I go through this in a couple examples, I'll show you a kind of a shortcut. So if the span of S, right, the set of all linear combinations of the vectors in S, is equal to set W, right, subspace W, and the set S is linearly independent, right, and I'll hopefully refresh your memory as to what that means. I'm assuming you know what it means for a set of vectors to be linearly independent. Well, if the vectors in S are linearly independent, that means you cannot write any vectors of S as linear combinations of other vectors of S. So that's the amount of vectors that is necessary to have its span be equal to W. So if S is linearly independent, then S will be considered a minimal spanning set of W, and you'd be finished. But if S is linearly dependent, that means that there's at least one vector in S that can be written as a linear combination of other vectors in S. So we'll go through this procedure. We're going to find a vector in S that can be expressed as a linear combination of other vectors in S. Remove this vector, and you'll get a new set, which I'll call, I called it T on the previous page. Here it's S prime, right? It's a different set. So this is the set without that vector from the previous step. So it's a smaller set. And then I ask the same question. Is this set linearly independent, this S prime, or linearly dependent? If S prime is linearly independent, then S prime would be a minimal, I know I didn't write S prime here, but then S prime would be a minimal spanning set of W. But if S prime is linearly dependent, then I start this process over here where it's linearly dependent. I'll find a vector in S prime that can be written as a linear combination of other vectors in S prime. I'll remove that vector and get an even smaller set, maybe called S double prime, and then ask the same question. And I keep doing this until I get a linearly independent. That's the goal here, is to get down to a linearly independent set of vectors whose span is equal to W, and then that linearly independent set will be called the the minimal spanning set of W. All right, so we just if we have a linearly dependent set, we're just going to keep removing vectors until we get the smallest possible number of vectors that are linearly independent and span W. I hope that all made sense. Again, I'm assuming you know what a span of a set of vectors means and what linear independence and linear dependence means for a set of vectors. All right. So the rest of the video is just me doing several examples of, I'm given a set S and a subspace, which is just the span of S, right? The set of all linear combinations of the vectors of S. And we're just going to determine whether the given set of vectors S is a minimal spanning set of the subspace. And if it's not, I guess I should add to these instructions, okay? So determine whether the given set of vectors S is a minimal spanning set of subspace W. And I'll put at the end here, I'll add some instructions to this. If not, find a minimal spanning set of W. I'll add those instructions as well. All right, so here, S. I'm gonna work in just with for all the examples in this video. I'm working with vectors from R2, two-dimensional space, the Euclidean plane, and R3, right, Euclidean 3D space, because those can be visualized on websites or whatever if you want to do that on your own. But what I apply here, though, could be applied to other Euclidean space, R4, R5, R6, or even other general vector spaces. I might get to a video later where we do it in general vector spaces, other vector spaces other than Euclidean spaces. All right, so here I'm given a set S of vectors in R2, right, 0, 2, and 1, 4. And W is the subspace here is the span of S, right? So W is all of the linear combinations of these two vectors, right? So every vector in W is a scalar times 0, 2 plus a scalar times 1, 4, right? That's what it means to be the span of a set. All right, the question is, is S a minimal spanning set of W? Right? Or is there a smaller set? Right? So if I, could I remove this vector and just say, 0, 2, just the set with 0, 2 spans W? Or could I remove this vector and say just the set with 1, 4 spans W? Right? Okay. Now, I've put up a video before on determining whether or not a set of vectors is linearly independent or dependent. So remember, again, if you've seen it. If not, I'm just going to kind of refresh your memory really quickly here. This is a set of two vectors, and these vectors are not scalar multiples of one another, right? 2 times 2 is 4, but 0 times 2 is not 1, right? And 1 times 0 is 0, but 4 times 0 is not 2, right? You can't find any scalars that you can multiply these by to get each other. So these two vectors are not scalar multiples of one another. I'll just say not scalar multiples, meaning that S is independent. This set of vectors is linearly independent and if you recall my previous page, this would mean that this set S is the minimal spanning set for the span of S. S is a minimal spanning set of W. All right. So that is one way, again, real quick when there's only two vectors in the set and they're independent. So what this means is that there's no smaller set that's a subset of S, right? So I can't just take 0, 2 and say 0, 2 spans W, and I can't just take 1, 4 and say the set 1, 4, spans W, right? Now another way to do this. Okay, another way to do this. Remember the on the previous page with the procedure. The question is about whether or not the set of vectors that spans W is linearly independent or linearly dependent. So if you recall how to check for that, right? So we're going to, say I didn't remember this, all right? This is another way to approach this. We're going to, this is the way we're going to start with all these. We're going to check for independence or dependence. I'll just say check for independence. Now recall how to check for independence. What did it mean for a set of vectors to be linearly independent? We were looking at this equation. Some scalar, I'll call A1 times the first vector in S plus some scalar times I'll call A2 times the second vector in S. Remember, we're saying when is this going to be equal to the 0 vector? Right, the vector 0, 0. All right, and what I have here actually boils down to solving a system of linear equations involving A1 and A2. Right. So solving this equation for A1 and A2 here results in this system where if I look at the first components, it's just A2 equals 0 for the first components being equal. And then for the second components to be equal, I need 2 times A1 plus 4 times A2 to be equal to 0 as well. And I mean, it's obvious here that the solution to this system, A2 must be 0 clearly. And if A2 is 0, then this term would be 0, and then you'd have 2 times A1 would be 0, so A1 would have to be 0, so A1 would have to be 0, A2 would have to be 0. And remember, when all the scalars are 0, and that's the only solution, this is called the trivial solution. Right, when all the scalars are 0, that's an obvious solution, right? If you let all the scalars A1 and A2 be 0, you're definitely going to get the 0 vector in this equation. But only the trivial solution is a solution to this. And remember how we define linear independence and linear dependence. If this equation where you have a linear combination of the vectors in S equal to the 0 vector, if that has only this trivial solution where all the scalars are 0, then S is linearly independent. So I come to the same conclusion as earlier, right, when I talked about a set of two vectors, and if the vectors are not scalar multiples. you can jump to the conclusion that the set of vectors is linearly independent. All right. And then I jump to the same conclusion. Since this set of vectors is linearly independent, that means that I need both of them, right? I need both 0, 2, and 1, 4 to be able to span W, sorry. Because I can't write one of these as a linear combination of the other. Right? I can't eliminate one of them. I need both of them. Okay, another thing. So I could also do this, right? Or, and we'll eventually get down to a very quick way, and I'm going to do this for the first couple examples, maybe the first few. I've got several here. Or you could also look at this as like a matrix equation, remember? And I write an augmented matrix for this. Where down the first column I have the coefficients of A1, which are 0 and 2, right? 0, A1, 2, A1. Or that's just the first vector in S, right? 0, 2. And the second column is the coefficients of A2, 1, 4, which is just that second vector from S. And a little bar, and then 0, 0. And then I put this in reduced echelon form or reduced row echelon form using some row operations or a calculator. And I'll be using the calculator plenty later. I'm not going to do it for this one because it's pretty simple. There's only 2 rows. And also another thing I'm going to point out that I'm going to do in a future example. This row here, when we're checking for independence, the system is always going to have zeros on this side. I have a linear combination of the vectors in S equal to the 0 vector. So this will always be zeros, no matter what operations I perform, right? Add rows to other rows and multiply rows by stuff. This will always be a column of zeros. So in the future, I'm just not going to write this, right? We're just going to look at the coefficient matrix only. And let's see what this looks like, when I put it in reduced echelon form or reduced row echelon form, labeled RREF sometimes, on your calculator especially. Well, I would switch the rows so I get this, non-zero entry in the upper left-hand corner. And to make that a 1, I would multiply all that by a half. Right, and so then this row would be down here, 0, 1, 0, right? And then up here I'd have 1, then 2, but then I can eliminate the 2 by multiplying the second row by -2 and adding it. So I get 1, 0, 0, 1 over here. And again, like I said, this is always going to be zeros. So I'm really only focusing, right? And in future examples, I'm really only going to be focusing on the coefficient matrix. Right? Focus on the coefficient matrix. Sorry, coefficient matrix. All right, and what you're going to notice, and it's it's a very short example to start, very small one. I mean, if you look at this, remember this means that A1 equals 0, this row, and this one means A2 equals 0. Exactly what I got up here, right? So that's that trivial solution, again, meaning that S is linearly independent, therefore S is a minimal spanning set of W, right? A minimal spanning set of the span of S. But one other thing I'm going to point out here is that if you look at the coefficient matrix, when you put it in reduced row echelon form, the pivot columns of the reduced echelon form will correspond to the vectors, the independent vectors from S. And I'll put that up here. I'll write that little note down here. And again, I'm going to do this on a lot of examples, so if you're not seeing it right yet, just bear with me. All right. So we're going to notice here that the pivot columns of the reduced row echelon form matrix will correspond to the vectors of S that are independent. To the vectors of S, right, which are going to be, the same column of the coefficient matrix, columns of the coefficient matrix. Pivot columns of reduced row echelon form will correspond to the vectors of S that form an independent set. Or a linearly independent set. All right, and that's huge. All right, so you see here how when I put the coefficient matrix into reduced echelon form, the first column is a pivot column. So the first vector, 0, 2, this first column of the coefficient matrix, is part of and also the second column is a pivot column. All right, so the first two columns are pivot columns, so that means the first two vectors of S, so the first two columns up here, 0, 2, and 1, 4, form an independent set, which we've already said, right? The whole thing, right? Vector 0, 2, and 1 form a linearly independent set, and therefore will give you a minimal spanning set. Form an independent set, therefore a minimal spanning set for the span of S. Lots of stuff to take in here. All right, huge. Okay, so going to another example. All right, I showed you 3 different ways how you can show that these vectors were linearly independent, and therefore a minimal spanning set for the span of S. Right, a minimal spanning set for W. All right, well, next example, I'm doing the same instructions. Okay, given another set of vectors from R2. Okay, so again, the same instructions. Determine whether the given set of vectors S is a minimal spanning set of the subspace W, which is in all these examples, W is just going to be the span of S. All right, so the set of all linear combinations of these two, so some scalar times this first vector plus some scalar times the second vector will be in the W here, will be in the span of S. And if it's not, right, if S is not the smallest spanning set of the span of S, then find a set that is, right? So, if this isn't the smallest, then a set with one vector might be, or maybe I don't know, a set with no vectors, the empty set. Not going to get into all that. All right. So, but if these two aren't the minimal, then probably a set with one vector will be. All right. As I mentioned, we can do that. We can see this a couple ways. So notice again here, this set has 2 vectors. All right. And when a set has only two vectors in it, it's very easy to determine whether or not they are linearly dependent or linearly independent. That's what we're checking for. Here, these 2 vectors, are they scalar multiples of each other? And the answer is yes. -1 times -2 would be +2, and 2 times -2 would also be -4. So this vector times a scalar, right, times -2 would be this vector. So I have 2 vectors that are scalar multiples. All right, and if I have 2 vectors that are scalar multiples, that means that S, right, the set of vectors, is linearly dependent. And what that means is that S is not a minimal spanning set for W, for the span of S. All right. So this means that S is not a minimal spanning set for W, for that span of it, for the span of S, for W. So what is? Well, what we're going to see is that one of these vectors really is unnecessary. So remember that procedure I had up earlier? It was a while, second page now. If the set is linearly dependent, that means you should be able to find a vector that can be written as a linear combination of the other vectors. So, I mean, there's only two vectors here, so can you find a vector that is a scalar multiple, right, which would be a linear combination of the other single vector? And that's clear here, right? So again, I can take 2, -4 is equal to, -2 times the other vector, -1, 2. Right. So -2, 4 is a linear combination of -1, 2, right, or a scalar multiple of -1, 2. So that means you could also say -1, 2 is -1/2 times 2, -4. Just pick one though. All right. One of these can be expressed as a linear combination of the others. So what I'm going to do is I'm going to remove, because that means that this is unnecessary, right? That means that this is unnecessary. Because watch this, right? If you look at remember the span of S has here are the linear combinations of the vectors in S would look like this. You'd have some scalar times -1, 2 plus, and then some scalar times 2, -4. Well, so every single vector that looks everything that looks like this is in W, right? That's what the span of S is. It's a collection of all linear combinations of the vectors of S. But I just told you that 2, -4, depends on -1, 2. So this is the same thing as A1 times, -1, 2 plus, and then if I replace 2, -4 with, -2 times the vector -1, 2, I'll have -2A2 times -1, 2. And do you see how both of these now have the vector -1, 2 in it? So I could like factor that out. Remember how vectors in a vector space distribute over scalar addition? And then I'd have the scalar A1 minus 2A2 in front. And do you see how every linear combination of these two vectors is really just a linear combination of this one vector, a scalar multiple, right? This would be a scalar, A1 minus 2A2, of just a single vector. Right? So the vector, that means one of the vectors, the vector 2, -4, is unnecessary. So I'm going to remove this vector 2, -4 from set S. From S. And that makes this new set, which again I called on the page with the procedure, I called that S prime. And I get, if I remove 2, -4, I get just the set with -1, 2. And then I can start over if I wished. And then the question is now I start over, is S prime linearly independent or linearly dependent? Right? And the answer is yes. It's a single vector. And again, if you go back to my video on checking for linear independence or linear dependence, if a set has one non-zero vector, which this is, it's linearly independent. So this set, S prime, is a minimal spanning set of W. Okay, and then some other stuff we could write related to this too is this. We could say then that the span of S, so then the span of S would be the same as the span of S prime, right? Or the span, if I actually write out the vectors, the span of that set with -1, 2 and 2, -4 in it would be exactly the same as the span of the set with just -1, 2 in it. All right, and we saw that over here. right? I showed you that over here with these linear combinations. This is the set of all linear combinations of -1, 2, and 2, -4. And we saw earlier that every linear combination of those two vectors is simply a linear combination or a scalar multiple of this vector, which is what this set is. This set is the all linear combinations of -1, 2, right? Or all scalar multiples of -1, 2. So that like reduces the spanning set, right? And we have our minimal spanning set, a set of one vector that spans the same set as this set of two vectors did. Right. Okay, so that was one way to approach this. Remember OR. And I'll do the same thing I did last example. I'll do it a couple ways, right? Now, say I didn't remember this. Here I kind of did a shortcut because this set only had two vectors in it. Suppose I didn't remember that, right? Remember the first thing we should be checking for is, is this set of vectors that spans W, that makes up the span of S here, is the set independent or not, right? So is S independent or dependent? So remember how to check for independence. We're looking at this equation, right? I have a linear combination of these two, right? A1 times -1, 2 plus, and then A2 times 2, -4. And I'm asking, when is that equal to the 0 vector? Right. And this leads me to, I'm trying to find, A1s and A2s here that aren't 0 and 0, right? If 0 and 0 are the only solution, then S is independent and you have your minimal spanning set for W. But if there's a non-trivial solution, then S is dependent. Now, based on what I said earlier, there should be a non-trivial solution here. So remember, this corresponds to a system of linear equations where the first one, looking at the first components, I have -A1 plus 2 times A2 must be equal to 0. And looking at the second components, 2 times A1 minus 4 times A2 must be equal to 0. All right, and again, I could just look at the augmented matrix for this. -1, 2. Again, just that first vector in the first column, the coefficients of A1, and then 2, -4 in the second column. Bar with some zeros. Again, in a future example, I might not be putting these zeros because these will always be zeros. And then I put this in reduced. I could have solved this here on its own with like elimination or substitution or something. But I'm going to go and put this in reduced row echelon form, which again would be pretty simple here. I'd multiply that top row by -1, or multiply it by 2, and then add it to this row to make a row of zeros. Okay. And then up top, multiply that by -1 to make that a lead 1, right? 1, then -2, then 0. And look at this. All right, you see that there's a pivot column. All right, so A1 is a basic variable. Oops, can't spell. That's basic, sorry. And then the second column is not a pivot column. All right, so A2 is free. All right, now because A2 is free, I can let A2 be whatever number I wish. And you can leave it as A2 if you want. I personally like representing free variables with other expressions, parameters, right? So I'm going to let A2 be equal to, say, T, where T is any real number. All right. And you can let a free variable be represented by any expression with any variables, as long as that expression can take on any real number value. And what we're getting from here is that, look at the first row, that's A1 minus 2A2. So that's A1 minus 2T, right? Remember, I let A2 be T, will be equal to 0. So A1 equals 2T, and A2 equals T, right? And here's a description of all the solutions, and you see how there are infinitely many solutions. Infinitely many. I can replace T with anything I want and get a solution to this equation. So because it has infinitely many solutions, there's definitely more than just 0 and 0 for the solutions to this. There's more than just the trivial solution. So S, the set of vectors we had, is linearly dependent. All right. So because of this, right, S, because there are infinitely many solutions, S is linearly dependent, as we mentioned earlier. So that means that S is not, again, I'll say it one more time here, S is not a minimal spanning set of W. So we have to remove a vector, and then see if that newer set is a minimal spanning set. All right, so how do I remove a vector, right? That's what I'm saying. I find a vector that is a linear combination of the others. Now I know, again, there's only two here, but that's where the non-trivial solutions come in. All right, if I look at the solutions to this system, say I let t be equal to 1. You could have t be anything you want. Just don't have t be 0, because if t were 0, that would give me the trivial solution, and I don't want that, right? Here's a non-trivial solution. And a non-trivial solution will help you in finding a vector that can be written as a linear combination of other vectors. So say t were equal to 1. Then you'd have a1 equals 2, a2 equals 1. And then going back up to this equation here, we'd have this. Right? I'd replace a1 with 2. You'd have 2 times the vector negative 1, 2. Plus 1 times the vector, so just the vector 2, negative 4, is equal to the vector 0, 0. And this is how you can find them. Any vector that has a non-zero coefficient or a non-zero scalar in front of it, you can solve that for that vector. You can get that vector in terms of the other ones. So I could solve for vector negative 1, 2, or I could solve this equation for vector 2, negative 4. And I'm going to do what I did earlier. I'll solve for this vector, get it alone. Right? So in order to do that, I'm going to just, this is positive 2 here times this. I'm going to subtract 2 of that vector to both sides. And, this is just a 0 vector over here, so it's not going to affect anything when you add. And I'll have 2, negative 4 equals, subtracting this equals negative 2 times negative 1, 2, which is exactly what I had up way earlier. All right, way back here, 2, negative 4 equals negative 2 times negative 1, 2. But I found it using some non-trivial solution to that, independence equation, that check for independence, where I have a linear combination equal a 0 vector. All right, so that means I don't need this, right? When I'm looking at the set S, any linear combination of these two will just be a linear combination or a scalar multiple of this one. I can remove this from S. And that gives me, again, a new set called, I'll call it S prime. It'll be this negative 1, 2. And then I start over and I ask, is S prime independent? And this time the answer is yes. And like I said earlier, this set here is the minimal spanning set, right? I wrote all that junk way earlier. So S prime, right? This vector with this set with just vector negative 1, 2 in it is the minimal spanning set for W, right? So the span of these two vectors is the same as the span of this vector. All right. Now, the fast way. This has all been well and good. Remember when I put things in reducible echelon form? Or, again, here's that coefficient matrix from the system, way back up here. All right, here was the system that was related to this equation when I was checking for independence, right? The coefficient matrix is just to the left of the bar here. Right, this is the coefficient matrix, and then you'll just remember you got zeros on the other side. The coefficient matrix was this, just made up of the vectors -1, 2 down the first column, and then 2, -4 down the second column. I guess I shouldn't put this because just a bar, because there'd be zeros on the other side. And I put this in reduced row echelon form, and you've already seen it, right? That was this vector here in reduced row echelon form: 1, -2, 0, 0. Right. Okay. And you'll see when you put the matrix in reduced row echelon form, again, remember the pivot columns in reduced row echelon form, right? Here's a pivot column. So this corresponds to a set of independent vectors from S, right? The pivot column, the first column, corresponds to your minimal spanning set, right? So the set with just the vector -1, 2, right, which corresponds to that first pivot column when you're in reduced row echelon form, is a minimal spanning set. For W. And it's really that quick. Okay, I know I did a lot of stuff earlier that took a while. But yeah, it's really that simple. I take my coefficient matrix, which is again just made up of the vectors of S, put it in reduced row echelon form, and whichever columns of reduced row echelon form have a pivot, those columns, those vectors from S, will make up the minimal spanning set, a set of independent vectors. Okay, great. All right, so that's what I'm going to do from here on out. All right. Now I do say here that it is a minimal spanning set, not the, because this set, this vector is good, but this one would also be good. -2, 4. I mean, it's only going to have one vector, right? I said minimal. This is a set with one vector that's minimal, so there's no set with less than one vector. That's going to be a spanning set for W as well. But really, any multiple of this would also be is also, if you take you could take any scalar multiple, -1, 2, right? Because any scalar multiple of this vector will also be a scalar multiple of this vector, right? Because they're scalar multiples of each other. Is also a minimal spanning set for W. So just know that spanning sets are not unique, and I think I've mentioned that in a previous video if you've been watching, and I'll make that note down here. Spanning sets are not unique. Okay. So if you go through and work something out, now if you follow this procedure here with the reduced row echelon form, you're going to get the same minimal spanning set as everybody else who sets up the same matrix. But if you go through a different process, I could have eliminated this vector instead, right? Because you can write 2, -4 as -1/2 times -1, 2. You can write this vector as a linear combination of that one. So I could say the vector 2, -4 instead, a multiple, which is again a multiple of this, is also a minimal spanning set. So answers will vary, right? But it's not spanning sets are not unique, right? But what I'm going to do is going to basically, if you follow my procedure with the matrices, you're going to find the same minimal spanning set as everyone else who sets it up the same way. All right, wonderful. All right, so I've shown you a couple of the long ways to do stuff. Let's just stick to that matrix way, all right, with the pivot columns and all that. All right, so here's a set S. It's got these, 3 vectors, 1, 3. Pardon me, -2, -6, 4, 12. And again, we're looking at this W is the span of S, right? All linear combinations of these. All right, well, you might be able to tell from looking at this, see how this vector is just -2 times this one? so I don't need this one. And this vector is just 4 times this one. So I don't need this one either. What you're going to notice is that, I'm basically going to end up with just one vector for the minimal spanning set. All right. Yeah, so I'm going to do the thing where is S independent? I'm going to just jump to the part where they make the matrix, coefficient matrix for that. You could write out the equation, set up the whole system and everything, but what you're going to end up is with a matrix like this, a coefficient matrix like this, with 1, 3 down the first column, -2, -6 down the second, 4, 12 down the third, and then a little bar, and then some zeros. But again, I don't need to write the zeros. You can if you want. Right? And then I'm going to put this into reduced row echelon form. Again, this one's pretty simple because if you take -3 times the first row, add it to the second row is made up entirely of zeros. And so you'd see there's only one basic variable, right? A1, the first scalar would be a basic, and then there's 2 free variables. I'll even mention this off to the side. The number of free variables will be the number of vectors you remove from S. Right. And in fact, the non-pivot columns will correspond to the vectors that you remove to get a minimal spanning set. But here's a pivot column, right? Pivot 1, and that's the first column, so that corresponds to this first vector from S. All right. So what we've got here is the set with just the vector 1, 3 is a minimal spanning set for W. It's that simple. Minimal. Or we could also say that the span of S is equal to the span of just the set with this vector. Right. Right, because every linear, what I'm saying here is that every linear combination of these three is just a linear combination of 1, 3, is just a scalar multiple of 1, 3, and I can show you that on this next page. Let's take a linear combination of these 3 vectors. So I have some scalar times 1, 3 plus some scalar a2 times -2, -6 plus, and then some scalar a3 times 4, 12. And as I mentioned before, we'll leave the 1, 3, right? We're sticking with 1, 3. But -2, -6 is just -2 times this vector. So I'd have -2, if I pull a -2 out of these, I'd have -2a2 times the vector 1, 3. Plus, and then, this 4, 12 vector is just 4 times this vector. So I pull a 4 out, 4a3 times the vector 1, 3. And look at this. Every single one of these has the vector 1, 3 in it. I can factor that out, and I have a1 minus 2a2 plus 4a3, right, which would be a real number. This would be a scalar times the vector 1, 3. So do you see how every linear combination of these 3 vectors from S is just a scalar multiple of 1, 3? So that's why we can say that the span of S is the same as the span of the set with 1, 3 in it. And 1, 3 is the minimal spanning set of the span of S, which was, W. Wonderful. All right, and again, it's really that simple. Just set up a matrix where the columns are the vectors from S, go to reduce row echelon form, and every column that has a pivot will correspond to a vector that is going to make will correspond to vectors that make up an independent set, and those will be the vectors of the vectors of a minimal spanning set for the span of S, right? The span of the original set. And then the two non-pivot columns correspond, where the free variables are corresponding. The two non-pivot columns will correspond to the vectors that you would remove, right? The vectors that depend on other vectors in the set. All right, so this, I got several more of these, and again, this should be quick now that we have this procedure down. All right, so here, S is -1, 2, 2, -1, 1, 1. Again, some vectors from R2. W is the span of S. So, W is made up of all the linear combinations of these three. And the question is, is this a minimal spanning set for W, right? Or is there a smaller set of vectors that also spans W, right? That equals the span of S. All right, so again, I would ask, are these independent? I'd set up that equation where I have, A1 times this plus A2 times that plus A3 times that equals the 0 vector, right? 0, 0. And then, set up the corresponding system, and finally this matrix. -1, 2 down the first column, then 2, -1, then 1, 1. Then you have a bar, and then you'd have zeros over here. And I'd put this into reduced row echelon form. Now, so far I've been doing it, in my head, because there's only been 2 rows, right? It's not been awful. But this time I'm going to show you the calculator. I mean, again, I could do it pretty quickly because it's only 2 rows, but let me show you the calculator. I'm going to just pull this up because, let me clear that. And so I go second matrix. This is TI 83, 84 plus here. They both work in a similar fashion. Go over to edit, and I'm making a 2 by 3 matrix here. This coefficient matrix, so a 2 row by 3 column. Enter the entries. The first row is -1, 2, 1. Second row, 2, -1, and 1. All right, and then let's get out of here. Quit. And then on the main screen, if I want to put a matrix into reduced row echelon form, I go over to the math menu and go to the matrix area, go over to the math menu, scroll up or down to B, this is RREF, which I've been writing right in capital letters. Don't confuse it with REF. That's just plain echelon form, row echelon form. So I go RREF, second matrix, and then, oh yeah, I want the names. I want matrix A, this 2 by 3 matrix A that I entered, and close it, and there you go. All right, so this is 1, 0, 0, 1, and then 1, 1. And again, you'd have zeros on the other side, which I'll use in a second. All right, just remember that there are zeros over here, technically, when you're trying to test for independence. And I look at this, reduced row echelon form. The first column has a pivot, right? Has one of these leading ones. The next leading one in a row is in the second column. So the first column is a pivot column, meaning that the first vector in S, and the second column is a pivot column. So the second vector in S, these two vectors here, will form an independent set that also spans W. Right. So I can jump now to saying that this set here, the set with -1, 2, and the set and the vector 2, -1. Right, this set of vectors, again I'll call this S prime, is a minimal spanning set for the span of S, right, for W. Great. You could also say that the span of S, right, the span of these 3 vectors, is equal to the span of S prime, right, just these 2. So that means that every linear combination of these 3 can be written as a linear combination of just these 2. One of these is unnecessary, the 1, 1, right, which corresponds to the non-pivot column. And let me show you that, right? So let me actually go in for some solutions here. You know, the A3 would be a free variable, so I'm going to let A3 be equal to T. Right, like I was doing before, right? Just represent it by something that can take on any real number. And from the first row here, we'd have, you know, A1 would have to be equal to, you know, negative T, right? Because A1 plus A3 would be 0. From the second row, we have A2 would also have to be equal to the opposite of T, because you have A2 plus A3 equals 0, or A2 plus T equals 0, subtract T. And then, like I said, I'm having A3 be T. So this describes all the solutions. Right, so definitely infinitely many solutions when I'm checking for dependence or independence. So it's, you know, this set is definitely linearly dependent, right? So set S is linearly dependent because you're seeing that this would, you know, you could pick T to be anything. And this would have infinitely many solutions, not just the trivial solution. Right. And then let's just see, how do I express, you know, since I've eliminated 1, 1 here, let's see, how do I express 1, 1 as a linear combination of these two? All right, so I'm going to go to the next page and pick a value for T here. All right, I'm going to say let's let T be just 1, just something so that I don't get the trivial solution. All right, so if T equals 1, then A1 would be negative 1, A2 would be negative 1, and A3 would be 1, right? I'm just using the negative T, T. And so I'd have negative 1 times the first vector plus negative 1 times the second vector in S plus, you know, 1 times the third vector would be equal to the 0 vector, right, from that equation where I'm checking for independence. And then remember, I'm trying to remove 1, 1 here. I want to see how can I remove 1, 1. So I'm going to solve for this vector, get this alone. So we see that 1, 1 is equal to, and all I would have to do is add these two vectors to the other side. I've got negative 1 of this, negative 1 of that. I would just add them to both sides and we get negative 1, 2 plus 2, negative 1. Right? Simple as that. So then that shows me, then I can show you how is every linear combination of these three equal to linear combination, just a linear combination of these two. So let's take a look at, you know, linear combinations of these three. Every linear combination of these three would look like this. You'd have some scalar times negative 1, 2 plus some scalar times 2, negative 1 plus some scalar A3 times 1, 1. Well, using the relationship I just established here, we can replace 1, 1 with this sum here, the sum of these vectors 1, negative 1, 2, and 2, negative 1. So this is equal to A1 times, you know, negative 1, 2 plus A2 times 2, negative 1 plus A3 times, and then in parentheses, you know, I'm replacing 1, 1 with negative 1, 2 plus 2, negative 1. And can you see that when I distribute the A3 and combine the like vectors, right, the negative 1, 2 vectors and the 2, negative 1 vectors, I'm getting A1 plus A3 times the vector negative 1, 2 plus, and then A2 plus A3 times the vector 2, negative 1. And do you see how every linear combination of those three is equal to a linear combination of just these two, the negative 1, 2, and 2, negative 1, right? The A1 plus A3 is a scalar, A2 plus A3 would be a scalar. So the statement I made earlier about the span of S being equal to the span of S prime, right? The span of these three vectors is equal to the span of these two vectors is correct. All right, wonderful. All right, so now I'm going to totally skip out on what vectors do I remove, and how do I, sorry, I'm going to still remove vectors, but I'm going to totally skip out on now. You know, how do I express one vector as another? And let's just find simply that minimal spanning set. All right, because I got just a few more here. All right, so next S is this set of three vectors from, now I'm in R3. Okay, now I'm moving up to R3. Every vector has three components. and W is, the set of all the linear combinations of these three. Well, can I write the linear combinations of these three as linear combinations of less than 3 vectors, right? Let's see. So again, I'd ask the question, is S independent? So I'd set up that equation where I have a linear combination of these, equal to 0, the 0 vector, 0, 0, 0, and set up the corresponding system, which would lead me to this matrix. 4, 7, 3 down the first column, negative 1, 2, 6 down the second column, 2, negative 3, 5 down the third column, and a bar, and then there'd be some zeros over here, but that'll always stay zeros. And then I put this into reduced row echelon form, or just reduced echelon form. Now again, I go to the calculator here just to save some time. So second matrix, go over to edit, and this is a 3 by 3 matrix this time that I have here, the coefficient matrix. I got first row 4, negative 1, 2, second row 7, 2, negative 3, and last row 3, 6, 5. Okay, great. Get out of there. And then the last thing I entered in here was reduce row echelon form. So I'm just going to go second entry, which is above the enter button in blue, and it enters the last entry I made, right? And then I do that reduce row echelon form again. Okay. So this 3 by 3 in reduce row echelon form is, the identity matrix. So you see how the A1 would be 0, A2 would be 0, A3 would be 0. So the only solution to that equation would be the trivial solution, meaning that, this is a set, S is linearly independent. And remember before when I said, hey, if I have a set and we look at the span of that set, if that set is linearly independent, then that is the minimal spanning set for the span of that set. Right. Okay, so, and again, looking at the pivot columns, right, there's a pivot column, column 1 is, so this vector is going to be in my minimal spanning set. The second column is a pivot column, so this vector is in my minimal spanning set, and the third column, right, is a pivot column. So the third vector, like I said, if S is linearly independent, then S itself is a minimal spanning set for the span of S. So S is a minimal, and again A, because you could do any put in other vectors in here, have another set of 3 vectors that are linear combinations of these, and you'd have another minimal spanning set. S is a minimal spanning set of the span of S. All right, so I can't. So the span of S, I can't shrink that down to be equal to the span of some smaller set. Right? I could only write it as the span of another set of 3 vectors that are linear combinations of these, or 4 vectors, 5 vectors that are linear combinations of these, but nothing smaller than 3 vectors. Wonderful. That was a simple one. Next one. So again, another set of 3 vectors from R3. And I hope it's obvious that the first and third vector here are just negative 1 times each other. Right? So one of those is not going to be necessary, but we're going to see that here in a second. And then W is again the span of S, right? The set of all the linear combinations of these 3. Now the question is, can linear combinations of these 3 be written as linear combinations of a smaller number of vectors? And this time the answer is going to be yes. Now remember, I would check for independence. I'd set up that equation where I have a linear combination of these 3 equal to the 0 vector, and set up the corresponding system and then the matrix for that system. Now the coefficient matrix would have 1, negative 2, 0 down the first column, 0, 0, 1 down the second, negative 1, 2, 0 down the third, and then a bar, and then I'd have zeros over here, but I don't really care about that. Just look at the coefficient matrix. I go put this in reduced row echelon form, or reduced echelon form, and again I'm just going to go to the calculator for this to save some time. So back to the matrix, edit, it's still a 3 by 3. First row 1, 0, negative 1, Second row, negative 2, 0, 2, which you see is just negative 1 times the first row, right? And then the last row, 0, 1, 0. Right, and again, back on the main screen, just going to hit entry again for reduce row echelon form, and look at that, right? It's 1, 0, 0, 0, 1, 0, negative 1, 0, 0, and then again zeros on this side. So you could say, hey, look, the system's going to have infinitely many solutions because there's a free variable. All right, and that free variable you could say also corresponds to the vector you're going to remove, or the pivot columns, right? This is a pivot column, this is a pivot column. These two correspond to the vectors I'll keep in it. All right, these two vectors, right, corresponding to the pivot columns, the 1, negative 2, 0, 0, 0, 1, those form a linearly independent set that would also span W, right? So I'll call this, S prime, which is just the set of negative 1, 2, 0, or sorry, 1, negative 2, 0, 0, 0, 1. This set, right? Every linear combination of these will give me the same thing as the linear combination. Every linear combinations of these three, right? Or you could say every linear combination of these three can be written as just a linear combination of these two, right? Because we should be able to express negative 1, 2, 0 as a linear combination of these two and then get rid of it, right? So this is a minimal spanning set of W, right, of the span of S. We could also say that the span of S, right, the span of these three vectors will be equal to the span of S prime, right, the span of just these two. As I was saying earlier, every linear combination of these three can be written as a linear combination of just these two. Wonderful. All right, and I have finally, last example, all right, just one more here. Here are 4 vectors from R3, and again, W is the span of S, right? So can every linear combination of these 4 be expressed as a linear combination of a smaller number of vectors? And the answer is going to be yes. Again, I don't know if you've watched my video on linear independence and dependence. Remember, when the number of vectors in a set is greater than the number of components that the vectors have, then S is dependent. All right, and I'll write that right now. I'm going to say S is linearly dependent. We are going to see this. So I'm going to need to remove some vectors. Again, the little shortcut reasoning that you might have seen in my other video is that the number of vectors is greater than the number of components in the vectors. 4 is greater than 3. So S is going to be linearly dependent, but let's check that out. If I was testing for dependence, I would say a linear combination of these equals the 0 vector. Does that have any non-trivial solutions? And I'd set up this matrix corresponding to that system with 1, 0, 3 down the first column, 2, 0, negative 1 on the second column, 4, 0, 5 down the third column, and then 2, 0, 6 down the fourth column, then a bar, and then some zeros over here. And I want to put this in reduced row echelon form. Now, obviously, there's going to be a row of zeros, right? This isn't changing. You just move that to the bottom, and we'll see how many free variables there are and how many basic variables, pivot columns, non-pivot columns. All right, so again, I'm going to go to the calculator here, second matrix. I'm going to just edit matrix A again. This is a 3 by 4 this time. All right. We have 1, 2, 4, 2 in the first row. Bunch of zeros. And then 3, negative 1, 5, and 6. All right, get out of here, do the reduced echelon form, row echelon form. Okay. we're seeing this matrix 1 0 0 0 1 0 2 1 0 and 2 0 0. Then you'd have again zeros on the other side if you want to, so there's definitely going to be infinitely many solutions to the equation. So you're definitely saying that S is linearly dependent. Well, look, there's only two pivot columns, right? This lead one, and no other row has a leading one. So this is going to reduce down from 4 vectors to 2 vectors. All right, so instead of, this is nice, doing it this quick way with the reduced row echelon form, because the way I was doing it before, the long way I did it in the first couple of examples, you kind of have to work in, getting rid of one vector at a time. If this vector, this vector is a linear combination of these 3. So I get rid of that one, and then I look at these 3, and this vector is a linear combination of these 2, so then I get rid of that one. You kind of have to go through that procedure one at a time, which makes this a nice quick shortcut here. But hopefully you understand what's happening, though, right? Understand the long way before you can appreciate the short way. So I'll call this S prime is just the set of vectors with 1 0 3 and 2 0 negative 1. This set of 2 vectors is a minimal spanning set for W for the span of S. And you could also say that the span of S is equal to the span of S prime, or in other words, every linear combination of these 4 vectors can just be written, can be re-expressed as just a linear combination of these 2. Simple as that. All right. Now again, if I wanted to do it the long way, I could. It would be a little more tedious, and try to determine how do I write this vector as a linear combination of these 3, and then how do I write this vector as a linear combination of these 2, and then re-express everything as a linear combination of just these 2. But again, I'm just doing the kind of the shortcut way here at the end, just to save a little time. All right. So yeah, quick and easy. If you're given a set of vectors and then the span of that set of vectors, to determine if this is to determine a minimal spanning set for the span, just make a matrix, coefficient matrix with those vectors in columns, put it in reduced row echelon form, and then the pivot columns go back to the original matrix. The pivot columns in reduced row echelon form will correspond to the vectors of S that form an independent set, and thus a minimal spanning set for the span of S. Wonderful. All right, so I hope you have fun practicing problems on this, and thank you very much for watching.